How's it going, ladies and gentlemen? Mr. Donahue here once again. This time we're going to take a look at reaction rates. So our objectives will be to stoichiometrically determine the rates of disappearance or appearance of substances involved in a chemical reaction. All right. So what is reaction rate? Let's start there. What do we mean when we say reaction rate? So if this is our generic reaction, A plus B gives me C, the reaction rate is the speed of the chemical reaction. It's basically how fast does the reaction occur. So in this example, it could be how quickly is A or B being consumed because they're reactants, or how quickly is C being made because it's a product. So rate, again, is just change over time. So if we're talking about chemical reactions, we're talking about changes in the quantity or the concentration of a substance because we're making new stuff. So how quickly is that changing? So how quickly does the molarity of A or B decline because they're reactants, or how quickly does C appear over time? So average rate is just going to be the change in the thing we're talking about over time. So if we're taking a look at, substance A, initially at time 0, we have 0.1 molar, and we don't worry about the average rate because that's what we're starting with. But after 50 seconds, it drops to 0.090 molar. So what is the average reaction rate? Well, we take the change in the concentration. So this is our change in our concentration of 0.01, and we divide it by the time. And then we get 0002 molar per second. So that is going to be our average reaction rate for the first 50 seconds. Now, if we take a look at 100 seconds, the concentration continues to drop. So if we want the average rate for the first 100 seconds, you do the same process. You go, what is my change in my concentration? Which it's 0.019 molar. Divide by the 100 seconds, and you get the average reaction rate over that period of time. And then same process for the last one. Hey, it dropped down to 0.075 molar. So what's the overall change? 0.025 molar divided by 150 seconds. And you get the average reaction rate of 0.00017 molar per second. And you can see the reaction rate drops over time, right? So it's decreasing because we're using up these reactants, so their concentrations are dropping. So here's an example. Try it on your own, pause it, then press play once you think you got the answer. So for the following reaction, the initial concentration of Y is 1.5 molar, and after 150 seconds, it dropped to 0.8 molar. What is the average reaction rate for this period of time? So again, we need to get the change in the concentration divided by the time. So we go, all right, well, what was the change? I started off at 1.5, and I dropped down to 0.8, and that's going to be over 150 seconds. So that is going to be a difference of 0.7 molar divided by 150 seconds, and you get 4.67 times 10 to the negative 3 molar per second. So reaction rates over time. Let's talk about what happens to that. Reactions slow down over time. This is because the concentrations of the reactants decrease as they are consumed. So it slows down the rate of reaction. We're using up the reactants, so we have a lower concentration over time. Lower concentrations means slower reactions. So this graph shows concentration versus time. You can see the slope, that would be our reaction rate. So the slope would be, the change in concentration over the change in time, and that is our rate. So you can see the slope for these, the slope decreases over time, right? It's becoming flatter, slows down. So the instantaneous rate, if you were to take the slope of a tangent line to the graph, this would be the instantaneous rate for that time. So if I were to go, hey, at this point in time, what is my rate for right then? Well, you take the tangent line, and then you go, what is the slope of this tangent line? And that's going to be your instantaneous rate, the rate at that very moment. So if you were to do this at time 0, this would give you the initial rate because it is the rate at the very, very beginning. So if I go to time 0 and I draw a tangent line to that point, that's going to be my initial rate. How fast was that reaction at the moment it started? So reaction rates in stoichiometry. The rate of disappearance A is equal to the rate of disappearance B in this example. And the reason for that is they both have a coefficient of 1. They have the same coefficient, so for every 1A that gets consumed, I'm making 1B. So as A changes, B changes to the same amount. But if I looked at a different reaction, it's not always going to be that way, right? We have two X's, being used with every 1y, giving me 3z. So how is this going to affect our reaction rates? The rate of disappearance of x is going to be twice that of y because it's a 2-to-1 ratio. For every 2x, we use up 1y and we make 3z. All right, so the disappearance of x is twice that of y. It's going to disappear twice as fast as y is. And the rate of appearance of z is going to be 3 times that, the disappearance of y. For every 1y we make, or use, we make 3z. So let's work with this a little bit. Try these problems, see how you do, and then come back to it. All right, welcome back. What is the rate of rate of appearance of z? I always like to do this. Circle the one thing and then put a box around the other because it helps me focus. So what is the rate of appearance of z if the rate of disappearance of x is 1.5 molar per second? So I know I want to end up with the rate for z, right? And they give me x, so 1.5 molar per second for x. And I know that the ratio between x and z is 2 to 3. So I'm going to have to say for every 2x that gets used, I'm making 3z. So now I can just multiply this and go, hey, the x cancels out. And when I do that math, I end up with 2.25 molar per second. So this is for z. That's how quickly z is appearing if x is disappearing at that rate. How quickly is y being consumed if the rate of appearance of z is 0.75 molar per second? So again, they tell me 0.75 molar per second for z. I'm trying to get y, and I know that the ratio is 3z to 1y. So I multiply by 1/3. I get 0.25 molar per second in terms of y. So you can see y is going to disappear at 1/3 the rate of z appearing. So again, how fast is x being used up if y is being consumed at 1.2 molar per second? So I got 1.2 molar per second for y. And I know that between y and x, it's a 2-to-1. So for every 1y, I'm using 2 x's. So I multiply those together and I get 2.4 molar per second in terms of x. So that's how you do those things. So if the rates of appearance and disappearance depends on the stoichiometry, how do we specify what the reaction rate is? You know, we're not always going to say the reaction rate in terms of this particular substance. And if it's not specified, it's given as if the coefficient was 1. So if you're ever given a problem where it's like the rate of reaction was this, and it doesn't say in terms of anything, it's acting as if the coefficient is 1. So if this was my reaction that I'm working with, the reaction rate is going to be half the rate of the change of x over time because we got a 2 there. So we got to correct it to be as if we had a coefficient of 1. So x is going to disappear twice as fast as something with a coefficient of 1, so we got to times it by 1/2. For y, it does have a coefficient of 1, so the change in y over time is actually also going to be equal to the reaction rate. For z, I got to times it by 1/3 because it has a coefficient of 3. So z is going to change 3 times as fast as the reaction rate. So that's how you do that. So if I were to kind of generalize this, all right, where the lowercase letters are the coefficients and the capital are the species, it's going to be the change in that stuff divided by its coefficient over time. And you can do that for all of them, right? It's going to look to be the same kind of pattern going on. So there you go. So try some of these, all right? What is the reaction rate if the following is true? So the rate of x disappearance is 1.2 molar per second. Well, I got 1.2 molar per second, and I have a coefficient of 2. So that's going to tell me that the actual reaction rate, if I wanted to specify in terms of no particular species, is going to be 0.6 molar per second. All right, what if the rate of y disappearance is 0.5 molar? So 0.5 molar per second times, oh hey, once you know it, the coefficient for y is 1. So it's going to be equal to the same thing, 0.5 molar per second. What if the rate of appearance of z is 0.75? All right, so we got 0.75 molar per second, and we have to times that by 1/3 because z's coefficient is 3. So I end up with 0.25 molar per second. So summarize. Can you stoichiometrically determine the rates of disappearance or appearance of a substance involved in a chemical reaction? I hope you can. Otherwise, I failed you. I'm sorry. Okay, bye.